Today I'm gonna be doing a dynamic programming interview. So I have my friend Alpha again, who's gonna be testing me. Gonna ask me a few DP questions. You wanna quickly talk about how you're gonna format this interview?
Yeah, so I the easiest way for me is just I'm just looking at the NeetCode like 150 or 250, and we're gonna start with
Mhm.
some easy ones, and then depending on how you do, I'll kind of see which ones to ask you next. So we'll do
Nice.
2 or 3 questions, kind of depending on how you're doing, and
Yeah.
then the difficulty will kind of depend on how you're doing as well.
Cool. Sounds good. Yeah. Yeah. Let's just start from basics because I haven't done a DP question in a while.
Okay, okay.
So yeah, if I easily do it, then yeah, ramp it.
All right, so let's do this one first. This is like the standard easy one, and yeah, I'll let you take it from here.
Okay. Sounds good. So let me fix my screen here. Sick. All right. So we're climbing a staircase and it takes n steps to reach the top. Each time you can either take one or two steps. Pretty much in how many distinct ways can you climb to the top? So let's see this. Okay, it's already we have example 1 here and then we have example 2. So we have the first one which is 2. So how can we get to 2? We can either get there. There are two ways to climb to the top. You can either take like one step plus one step, or you could just straight jump to it. It's hard to visualize this, but it's like,
You can draw
or
it in the drawing if
yeah,
you
let me
want
draw.
as well.
You're right. You're right.
Cool.
Cool. We got a bunch of stuff here.
I get rid of that.
So let's do. I mean, n equals two. So
Mm-hmm.
pretend we want to. We have two steps. One, two. We want to get to. We want to see how many ways we can get to the second step. So if we start here, we could just jump right away, or
Mm-hmm.
we could like jump here and then jump here. That's why
Mm-hmm.
it's equal to two. Pretend we wanted to get three. Pretend we wanted to get three. We could have jumped we could have jumped from here, or we could have jumped from here, right?
Mm-hmm.
So I guess what we could like all we really need to know is if we're looking at a specific step, we just need to know. I mean, we could have got there from this step, or we could have got there from this step. Well, we kind of just if we knew, we could kind of do it top down where like if we knew how many steps it can get from here, and we also knew how many steps it possible ways it could get to this step. If we just add those up, then we know how many steps we have here, and we can kind of do that top down. Like we can look at it going backwards a bit. We can go like top down or bottom up. But let's see, because how many times can we get to this third step? We can either come out from here or come from here, and then we could just ask the same question for this guy. This is I'm thinking for the top down. It was kind of like, oh, we could have came from here, and we don't know how much times to come from, or we don't know how many steps. Like we'll have some base case here. Right?
Mm-hmm.
This would take 0 steps. And then from here, then we could have came from here, or we could have came like to 2 steps. So we could kind of ask that question, and then we can like recursively go down. But then, for example, if we already calculated because this will recursively go down. If we already calculated how many steps this we already calculated how many steps it takes to get here. When we ask that question for this guy, because this guy's gonna ask it for here and here,
Mm-hmm.
we don't need to recursively go down because pretend this is long. If we already calculated for the first guy, we only need to do that for the second guy, essentially. Or we don't need if we already did it for the first recursive call, we don't need to do that same work twice. If that
Yep,
makes
makes
sense, we
sense.
could quarter cache that.
Mm-hmm.
That would be like a top down approach. But then
Yeah.
That would be, I would think that would be around the O of n time complexity because for each of the steps we calculate it once.
Yeah, I'd say for when you're learning DP, I would just start with top down. Even there's like some slight optimizations you can make with bottom up, but I would just completely ignore bottom up. Be able to do
Okay.
90% of questions top down, and then you can look into bottom up if you want to.
Okay. Sounds good.
Unless there are rare cases where it's more intuitive bottom up, then I would go with that if it's more intuitive to you bottom up, but it's
Yeah.
very rare. So
Yeah. Yeah. That was kind of a. Let's see. How much time was that? Yeah. That was like I was trying to. I'm still. I was still trying to limit out for 20 minutes, so I kind of gave a terrible or try to solve the question really fast. So it's kind of a bad explanation.
mm-hmm.
But let me implement the code and yeah, maybe give you feedback on how I could explain that better.
Sure.
Let's see. So I think let me write out the function here.
Mm-hmm.
So what we're gonna do is we're gonna try to see how we're gonna try to climb the stairs. So we're gonna say let's just create a simple function called num stairs, and I'll break it out into others if it needs to be.
Mm-hmm.
Because we could do like a delete code solution with go solution.
Yeah, we don't need that. We don't need the leak code. You can just make a function. That's fine.
Okay, let's just do this in case we need to manage some state.
Okay,
Um,
sure.
but what we're gonna be given an n,
Mm-hmm.
right? So what is the n gonna what would do we need to do here? Let me load up this whiteboard. Basically, what it's gonna do is we need to handle base cases. So if n is equal to, we need to handle a base case. So if n is equal to 0, is there constraints? So I forgot to clarify as well. Is there constraints on n here? Can it be negative number? Can it be 0 or
So we'll
1?
just say it will always be positive. So it'll be at least like we'll just keep it simple. We'll just say it's two or more.
2 or more?
Two or more.
Okay. If it's 2 or more. Okay, if n is equal to 1, then we'll just return 1, right? Because there's only one way we can get to 1.
Mm-hmm.
If n is equal to 2, what is 2 here? Then return 2. These are base cases. Because there's two ways to get to 2. You could either just jump straight to it or jump like take 1 and then 1, right?
Sure.
So we handle our base case here. So now we're handling all these are anything n is greater than 2. And then basically what we can just return is self dot num stairs of like we can get there from taking n minus 1, which is plus n minus 2. Like I mentioned, we just need to add up how many times we can get from the stair behind us, just one step, plus the amount of stairs we can get like if we jump from the second stair, or like 2 stairs behind us. And this
Mm-hmm.
would be the brute force because we're recalculating sub problems here. Like what if I call it with n3 multiple times? So what I'd want to do is cache that. So I would just build like a simple recurse function. Self and like a cache. Put this in here. And what I do is like I'll cache the result for n, and then just return that value kind of thing.
Okay.
That and then what I do here is I'll basically just return self dot recurse. I'll pass n and I'll just pass in like an empty dictionary, and that's how I would cache the result. and then now I just need to save that. So, or I actually need to use that cache. So if n is in cache, return cache.
Okay.
So that will memorize it. I think that will get the result. Should
Yeah,
I dry run
I
it
think
or
so. Yeah, we could do a dry run. Yeah, I
okay?
haven't seen anyone write it this way before, but it makes sense to me.
Let's do yeah. Let's do 3 real quick.
Mm-hmm.
This is kind of how I do my DP problems. That's like maybe I
No, it's
suck at
totally
it.
fine. For one thing, people usually start at like 0 and go to n, not backwards. And for another, they usually don't make. I mean, I think this is better, but they usually just make like a helper in their original one. So, but this is fine too.
Oh, they start at 0 here.
Uh, I mean, they start at. Well, what I'm saying is like in here, they usually just make like a DP function and then call it, so it would all just be in one, and then they make a cache. But this is fine. Yeah.
Okay, I
Yeah, I
see.
mean
Okay.
either one works. Yeah.
Let's just start with n equals 3, and I guess we could like open this up like a recursion tree. N
Mm-hmm.
equals 3. So what is n equals 3? Since it's not equal to 1, it's not equal to 2, or it's not in cache.
Mm-hmm.
We can have our cache right here.
Yep.
Since it's not in there at all, we call n minus 1. So we actually call like n2 here,
Mm-hmm.
right? Since n is equal to 2, we just return 2 there. So this guy kind of like gets 2 right here. He's going to add another number.
Mm-hmm.
Then we call n minus 2. So we basically get n minus 1 here.
Mm-hmm.
N minus 1 is equal to 1. So we get like 1 here.
Mm-hmm.
And then now we store that in the cache. Say 3
Mm-hmm.
equal to 3. Right? Pretend we're calling this for like n4. Right. So this will call n3 here. This will call n3 here.
Mm-hmm.
So what's n4? N4, this will return 3, and then you'll return plus. And since 3 is already in the cache, when it calls wait, minus 1, minus 2,
Yeah, I think that needs to be
this
on
is 2.
two.
Yeah, since this is 2,
Mm-hmm.
2 is already in here, so I'll just return 2. That's 5.
Mm-hmm.
5. And we store that here. And like we could keep like going on that. But essentially like if we do like n5 here, it would be kind of the same thing where pretend yeah, it might get more interesting. Yeah, this will get more interesting after n5, I guess.
I mean, I think I get what you're like. I think you have the understanding down fairly well. So I think we can maybe
Okay.
stop at
Yeah.
this one. Sure.
So yeah, this will just return 3, and then you get
Mm-hmm.
5, and 5 plus 3 is 8.
Mm-hmm. Okay, so let's try running it on these, and then let's try a bigger number just to make sure we're getting the right thing, and then
Sure.
we can move on. But yeah, this was pretty
Yeah.
good, and you understood the cases very well. So
Solution. Let's do like 8. Do 5.
sure.
Let's just print. Or like if I was really try hard into it, I'd be like insert.
Okay. Well, do you know what it needs to equal?
I
Okay, it needs
think
to. I just
8.
ran on LeetCode. It needs to be 8. Yeah. So. Okay.
Was it ran? What if this was 7? Should insert.
I got an error. Oh, because you changed it.
Yeah, I changed it to 8. But like it runs if I do 8 here.
Mm-hmm.
Yeah, it was a classic DP one. But how was the
Wait,
explanation?
did it say successful or am I not seeing it?
It should say successful. Great. Well, it doesn't even run the second line. It would
Oh,
if I
oh,
move,
oh! I see. So
it just
assert
breaks.
if it doesn't show the result, it just throws an error if it didn't. I see.
Mhm.
Okay. Yeah. Okay. Yeah. No, that was good. Yeah. So the main things I'd pointed out. So once you recognize all DP is literally just state, a base case, a cache case, and a recursive case. Every problem just follows the same format. So that's all you got to think about. It's like, okay, what's my base case? How do I recurse to get down to it? And then, yeah, just storing in the cache. That's basically it. And then the other thing is, especially for 2D DP, you need to figure out like what's your time complexity quickly. So typically the time complexity is just going to be all your state multiplied by each other. So state 1 times state 2, whatever. So you want to think about like, okay, how big can these be, and then roughly what's that? Does that make sense if you have more states?
Yeah.
Okay, and then your space is usually also the state, and then you want to think about, okay, is my recursive thing in O of one or O of n? So in this case, it's O of one. So like that's why your time complexity is O of n, because you have n state, you have a O of one recursion, so you have O of one. If you had like a loop in here that went from like 0 to n, then it would be like n squared. So once you can
Okay.
quickly figure out like what's my complexity, the rest of this is literally just all boilerplate. You just change a few lines. Does that
Okay.
make sense?
Yeah, that makes sense. Yeah, let's get into a harder one then.
Okay, yeah. So let's do a harder one. So let's do. So I feel like house robber is kind of like the same thing. So let's get into another one, and we'll do this one. Yeah, I think this one. Yeah, we'll see how this goes. Or actually, let's just do, instead of that one, let's do this one.
I'll delete this for now then.
Let me copy it. Okay, yeah. So this is another like really common one. Let's go with this one.
Okay, let me read it over.
Mm-hmm.
You're given an array of coins representing coins of denominations 1, 5, etc., and an integer amount representing a target amount of money. Return the fewest number of coins that you need to make up the exact amount. If it is impossible to make up the amount, return -1. Let's
Mm-hmm.
see. So, let me format this a little bit. Okay, we're given different denominations, right? We're given, like, pretend we have a $1 bill, $5 bill, $10 bill, and
Mm-hmm.
we want to figure out what is the minimum number we can do. We can get to 12 to. I
Mm-hmm.
think the reason why we need to use DP is because we can't like greedily choose the biggest coin
Mm-hmm.
because that might affect our decision down the road. Pretend, I mean, let's try to come up with a better case. Pretend it was like, what's a case when um, we can try to craft a case. I think if I was trying, like the thing is, we already mentioned this DP, but I think the
Mm-hmm.
hard part was figuring out if it's DP also.
Mm-hmm.
The way I would do that is try to find a case where greedily choosing, because what I'm thinking here is like if we just keep choosing the largest denomination, what if we can greedily choose the largest denomination and actually get the result? Why do we need to use DP there? That's the thing I would be questioning.
Right. So can you think of a counter example for what you said, and then that
Yeah,
would be, yeah.
let's try like 13. Right,
Mm-hmm.
and my biggest number was like 9, or we had 9. We have like 2, 2. Oh wait, like we have twos. So it would take 3 to get here,
Mm-hmm.
or like pretend it's just 12 when we have 9 and 2,
Mm-hmm.
and then we had like instead. Or let me craft the case. This is, let me think.
Yeah. So just here. So just this. If you add one more number, or the, yeah, like. Like add like a 6 or even this. Yeah, this is good.
Oh yeah, let's add a 6. Let's add a 6. If we
Okay.
add a 6, we can get there with 2. But here, but if we took 9, then we took 11, then we took 1, that would take 3. So we can't just like
Hmm.
greedily choose that number.
Also, the really easy example is what if we have like this? We get rid of the 1. So now we pick 11, but then we can't solve it. So
That's
that's the other
true.
thing. Like the biggest one might not always solve it, and then yeah, and then
That's
yeah.
true, yeah.
So
Okay.
okay.
So I think that's how I kind of identify its DP.
Mm-hmm.
Um, if it since it is DP, then like you mentioned, let's just work through a top down approach.
Mm-hmm.
So let's see. I
Yeah. So can you
mean,
kind of like those things that I said? So you need the three things like the state, the base case, the recursive case, and then estimated
yeah.
time complexity, and then from there you can just code.
I think like when we call this function right on 12,
Mm-hmm.
what do we need? We need what are the different base cases that we need to do? I think it's kind of
Mm-hmm.
similar to the last DP question where I mean we have different denominations, right? We have let's go with this case two. Or let's go with this case, right? 12. Pretend these are denominations.
Mm-hmm.
I mean we like pretend how could we have got to this 12 coin? Right? I
Mm-hmm.
mean, we could have got by taking one. So that means this would have been a like F11
Mm-hmm.
because we could have took one coin to get there, or we could have took F7, right? That means that we jumped to this from 5. Like if we take 5 as a denomination, then we just need to figure out like if we take the coin 5, we just need to figure out what's the minimum amount here that what's the minimum amount that we could get the target of 7, and then the same thing here with 10, we just do like F2, right? We can kind of recursively do that top down from 12 and try to cache on this number. Basically, what we're going to cache is like F at like an N,
Mm-hmm.
and it's like the minimum, the min of like the different denominations I could have took to get there, right? Because we don't know which one, so we should try the different ones. We should try two, and some might not actually, like you mentioned, some we might actually not lead us to actually get to the right result.
Mm-hmm.
So we need to be able to capture the fact that like we took a denomination that didn't work. But essentially, what we're going to try to do is we want to choose the denomination that will minimize, like the children that we call is minimized, or the value that we get back after recursing is minimized. Does that make sense?
Yeah, yeah. So what would be our base case here, or yeah, like
I think the base case would just be the different denominations. Let me
well, I
see
mean,
here.
how do we know when we can stop recursing? Is like, right? So in your climbing stairs thing, you said like
Yeah.
when you're at this thing, return this thing. So it has to be like the denominations are what you're caching.
Mhm.
But or sorry, what do you mean denominations is
Sure.
like if I'm at one of these, that's
Sorry.
the base case?
Yeah, I guess the base case is essentially base case is like we need to get to 0 because we need to
Right.
get the total exact amount. So
Mm-hmm.
like if
Yeah,
f could
exactly.
actually get to 0, just like that's the base case. But if it gets under 0, that's an error.
Right. So we want to make sure that well, we can't like throw an error, but I guess if we want to think about what we return for these, so these are kind of like the two things where we want to stop, right? Either we get to 0 or under 0. And we're
Yeah.
trying to minimize the number of coins we're using. So what does it make sense to return for each of these? Like how do we ensure we never take this thing as our
Yeah.
solution?
I guess like when we're looping over the denominations, we just don't loop or we don't recurse if it's gonna get it under 0.
That's
But
fine. Yeah, sure.
and then what we'll do is we'll yeah, the base case, I mean, if it gets to 0, we just take 0 coins there.
Mm-hmm. Yep.
I think that works. And if when we take specific coins, we just kind of add one plus like the function call kind of thing. Because we're taking a coin, and but we need to add one to that function call.
Yeah. I think you got most of it.
Let me try implementing it.
Mm-hmm.
Class.
Yeah, it is also funny you're writing the LeetCode format because like if you ask us on an interview and you write like class solution with like the LeetCode stuff, that'd be kind of funny.
Yeah, I like to do it this way because I like to do the helper function.
Yeah, I think
So
that's also like cleaner Python syntax as opposed to just writing helpers in the functions. So makes sense.
def recurse self pass. So what we're gonna do is, what are we're gonna be given an n again, and we're gonna say return self. I mean, there's gonna
So we're given a coins array and an amount this
oh
time.
yeah, coins, and we're given an amount self dot recurse, and we're gonna be given the coins, the n, and like we know we're gonna be caching, so I'm just gonna throw that in so we save time.
Mm-hmm.
So what we're gonna do is, yeah, let's talk about the base case. If the n is actually equal to 0,
Mm-hmm.
then we return 0.
Okay.
Like if we probably don't want to recurse if it's less than 0. But what we're gonna want to do is we're gonna have to keep track of a minimum value. So let's do float infinity, and then eventually we're gonna want to return that min val.
Mm-hmm.
I think here we'll like if this actually equals float negative infinity. I mean, what do we want to do if it can't? Okay, we want to return -1 if it can't be made of those coins. So if
Yeah.
we recurse on that and it returns negative infinity, let's return -1. Or see, just go like this. We'll do
Yeah, I'd
result.
definitely save it in a variable. Okay.
Yeah, not to call it twice, right?
Mm-hmm. Well, it. Yeah, I mean it's gonna be cat. Well, oh yeah, you'll send the new cache, so then you will call it twice. Yeah.
So if the result equals float negative infinity, we return that. Otherwise, okay, that just handles that case. So what are we gonna do? We're gonna loop through the different coins, and we're going to try to figure out the values here. So for coin in coins,
Mm-hmm.
if n minus coin is less than 0, then we just continue. We don't want to deal with that case, right? So we don't want to recurse there.
Mm-hmm.
Otherwise, um, sub result. This is the result of the sub problem. We'll actually recurse now,
Okay.
and we don't need to really like we can just take the same coins over because it's not like it's like if they use the coin, like you can use coin one multiple times.
Mm-hmm. Yeah.
So let's just pass in the coins again, and then let's pass in n minus the coin now.
Mm-hmm.
Then we'll pass in the cash. We'll say min val equals the minimum of the min value here. I mean, okay, and then we're saying since we're taking the coin, we're adding here. So this signifies that we're taking a coin.
Okay.
So each of the subproblems is going to add one to them, but we have the min val here. Um, yeah, at the end, we want to also add the cash. So same thing here. We do cash of n is equal to cash of n is equal to the minimum val here.
Mm-hmm.
And then like if n is in the cache, then we return just the n cache here as well.
Other way, I think.
If n in, oh sure, sorry, you're right. If n is cache, then yeah, we take the cache and then we return n there. So we don't recalculate that.
Mm-hmm.
I think that should work. I don't know if you wanna should I dry run it?
Sure. Yeah.
Okay. It's like, let me send out a message to someone. How's that look so far?
Oh, looks pretty good. Yeah, no, I think you're getting this very quickly. And like I said, if you do top down, it's really easy. It's all the same stuff. So yeah, once you recognize the states, it's literally just it's gonna get harder once there's more than one state, and they're not so easy to find. And like you said, you have to recognize it's DP. That's also
Yeah.
not the easy part. But
Let's
yeah,
do a harder one then, because I think this one might work if we just copy and paste it. I don't know.
yeah. I mean, you have a small error. I think it's just this. Everything else looks
Oh
good.
yeah, sure.
Some slight things you can improve on is you can actually sort the array, and
I
then
see.
instead of continue here, you just break. Because then,
I
like, if this is too small, then all the next ones will be too small or whatever. But that's like some small stuff. Also, you can make so you were trying to avoid getting negative numbers. You can also make that a base case. You can just say if n is less than zero, just return infinity, and then that will
I
automatically
see.
like never use your thing.
I see.
So,
That makes sense.
but you
Yeah,
can do it your way too. Either one. Yeah. Okay. So let's look at.
yeah. So it's slightly harder.
Mm-hmm. Yeah, I'm trying to find a 2D one that's like not too hard.
Once you realize it's DP, that's the it makes it easier for sure, but that's the
Mm-hmm.
kind of the hard part.
Okay, maybe we'll go with this one. This one's not so bad. Yeah, definitely. Well, so I like to think of DP as basically like a brute force with a cache. So like if you can't think of, and also the other thing that you can kind of look for DP is whenever you have non-continuous chunks of items. So if it's continuous, you basically just always want to use like sliding window or 2 point or whatever.
Mm,
But when it's like I can pick what things I can take and what things I can't, and like I can skip over, then DP is basically just like a brute force with a cache. So then you can quickly figure out, okay, what's the time complexity here, and does this work? And then you can write that out, and then there might be something better, but that's like the default for anything that is like not continuous, if that makes sense.
yeah, that makes sense.
Yeah, so it's really common, yeah, for LeetCode, I guess. And yeah.
Okay, take a look at this last one.
Hmm. And then
Uh,
yeah, maybe we can do some like harder ones in a couple weeks or something once you do
yeah,
more
I need to treat.
that aren't
I,
obvious.
I definitely had. I'm realizing I had the basics. Like
Hmm.
that one yesterday was just a straight hard one, so it's hard. Like the
Yeah, I think
even
that one's definitely tougher than these. But you were saying like I don't even know if I could do DPA. I have the basics down pretty well. You can draw the tree. You understand like the reason for caching. So we can definitely like ramp it up in a few weeks. That's nice.
nice. Yeah. Yeah, I think I could solve that other one if I build up towards it. But it's like I haven't wrote a DP question in a while.
Well,
It's
most people who haven't done DP will even do that climbing stairs and will just get stuck.
okay.
So yeah, you're definitely not there.
Okay, so we're given two strings, text one and text two. Return the length of their longest common subsequence. If there is no common subsequence, return zero. Okay. A subsequence of a string is a new string generated from the original string with some characters deleted, and but you don't change the relative order. So let's look at this. For example, ACE is a subsequence of I see. A common subsequence of two strings is a subsequence that is common in both strings. So just look at the example. I'm not 100% understanding it, but if I read through the examples, I think it'll make some sense.
Hmm.
So we have A here, A here. Okay, the longest common subsequence is ACE because yeah, you can delete elements from either of these without and maintain the same order and still get like ACE. Or yeah, and you can build ACE. What are some other common subs? Let me look at some other common subsequences that
Hmm.
might be shorter. You know, like B would not be one. C and E would be one. Like CE would be one, but it's two.
Hmm.
And just straight E would be one, but like E
Yep.
would be one as well, right? So we're just trying to find the maximum one.
Hmm.
Then what I would think at first, what I'd be thinking is like, how would we know if it's greedy or not?
Hmm.
Let me think that.
Or what
Yeah.
would greedy even be, right?
Like one greedy approach maybe would be like, what if we just like, okay, A matches, so what if we choose that one right away, right? For this one, it works that we choose A.
Okay, A matches and then the next letters don't match. What do you do?
Like, what if like it's like D D D, um, like you like picking A there wouldn't be optimal. That's what I'm thinking. Or pretend it was like this, A.
I'm not seeing you writing. Let me restart it.
Oh shoot.
I'm just gonna refresh it.
Can you see
Okay.
it now?
Yeah.
So I'm thinking here is like a greedy way would be like, okay, we just match A and then we match it here. Like what we're making decisions, right? Like we can choose A, but then if we choose A, we're not we'll have to match it with A, and we miss out on all of these ones, right? Like how do we know we
Oh,
don't
I
need to
see what
put
you're
A in
saying.
the
So you're
result?
saying like, do I have to look for this letter or not? I see.
Yeah,
So you're based. Okay. Okay. Yeah. Yeah.
like the optimal here is like picking D or something, or picking D here and then matching it with D's D, and not actually like A.
Mm-hmm.
But if we put A up front, then we'd actually need to pick A. So that's why it leads to like you can't really just do greedy, because how do you know that we can or can't not choose A without, because it affects your future decisions. Because
Okay. Now let me ask you. So in your example, when the characters are the same, like the characters at a certain index are the same, is there ever going to be a case where you don't want to take that, or do you just always take it?
if the letters are the same,
Yeah, like if the first two letters are the same, let's say, would you just always say that's part of the match, or is there a case you could think of where you wouldn't?
if the first two letters, I would always take it because it's not going to really affect anything.
Yeah, exactly.
It'll just
So
always
yeah,
increase by one. But
yeah,
if
yeah.
this wasn't the same and it was somewhere down here,
Mm-hmm.
I would have to think twice because I'm already missing out on a bunch of characters
Yeah, yeah,
that I could match with eventually.
yeah, yeah. Yep. Okay, cool.
So what I'm thinking is there's a good one. I think I'm trying to see how we could do this top down.
Mm-hmm.
Well, I think the inputs to the function are going to be two substrings, right?
Two substrings, sure. Yeah.
Or two strings in general.
Two strings, yeah.
Strings should be like, it'd be something like this.
Okay. And then can we think of those things I was mentioning, like the base case, the recursive case, and yeah, I guess you already mentioned the inputs.
And like this, these are the inputs for sure. I think I'm trying to think of the base case. The base case would probably be if like we have empty strings here. Like we get down to the empty string.
Yeah. What if one's empty and one's not?
Yeah, that would also be a base case, but it'd be that it would be like an invalid case. Or
Why
what
would
do
it be
we return?
invalid?
Because you
Like
can't.
if
Oh,
I
this would
have
be
a
zero. Yeah, this would be zero still.
yeah, so if one of them is empty or
Yeah, one
both,
of
it
them
should
is
be zero. Yeah.
base case. Is one of them empty?
hmm And then kind of like what are the choices we can make?
Yeah. I guess what I mentioned was that, I mean, we could choose the element or we could not choose it.
Okay.
If we choose, or we can choose to include this into the result or
hmm
not. Pretend it's this case. If we choose to include this into the result, then we could skip all of these guys and just pass down into the child. Maybe okay, but we already used A, so we'll just pass into the child C. Like we'll have to pass in this guy. So we'll basically call it with like F. We'll call it. We'll remove that element, but we'll also for like when we call the child, We have to call it like this because we can't use all these ones, and we used a, so we can sort of store it like this.
Okay,
What do we
so
call it
with
here?
this approach, whenever you pick a character on the left, you're basically saying if I include it, I have to loop through the right. I have to figure out where it is, and then I have to get like a substring. So that's like oven. Is there
Yeah,
any other decision we can make that's faster?
like we could just maintain indices there.
Yeah, we can maintain indices, yeah, instead of making the substrings, but regardless, if we choose to pick this letter A, then we need to figure out like, okay, where is it approach in our next substring? And it could be at the very end. Um, so it's still gonna take a while. So is there like can we have a recursive process that's not like do we take this letter from the left and find it in the right? Can we do something else?
Yeah, I mean, I guess we could just simplify where we could just like pass down this guy with one less down.
Yeah, exactly. So we
Yeah.
can just say like, well, we're just gonna move one of these strings up one. Like
Yeah, I
it
see.
could be one, it could be the other, right? So if we take the A, like or maybe we'll take the A, but if we choose to like go down one of them, we'll pass down the next one. And we could have the other approach, right, where we take the first string and we move that down a character. Where we just say like we don't want the A. Does that make
Yeah,
sense?
yeah. So
Okay.
okay, yeah, that makes sense. So we have the base case and our recursive case. We take one
Mm-hmm.
or don't take it.
Mm-hmm.
By take one, we essentially need to. Well, it needs to. In order to take one, it kind of needs to equal.
Yeah. Well, yeah. So I guess there's two cases, right? So what happens if the first characters are equal? You already kind of mentioned this ahead of time when I asked you,
Yeah.
right? Like if
If,
they're the
if
same.
yeah, if it's equal, I mean, we just increment both pointers, but we need to add one because that means
Mm-hmm.
we can get a subsequence of one at least.
Yeah, yeah. And if they're not equal, then what are the choices we have?
I guess if it's one, we could just increment, and then there's no cases really. But if it's not, then we need to take the minimum or the maximum of like either moving this guy up
Mm-hmm.
or or moving this guy up or the other one, but like we either move this pointer up on the first string or
Mm-hmm.
the first pointer up on the second string or the second pointer up on the second string.
Yeah, exactly. And
Like
so we're
that.
not committing to taking something, but this is like we're shrinking the string, and we don't have to like search for where does this appear.
That's yeah, that
And
makes
then we
sense.
can also use pointers instead of substrings, so we don't have to like because I think yeah you mentioned this before in some of your interviews, right? Like if I take a character off of a substring at every iteration and make a new substring, that's oven as well, which is not good.
Yeah,
So you can use
that'll
an
be
index.
make it super inefficient. I
Mm-hmm.
think yeah, so we call it if we increment one pointer, and then we could just work with pointers here,
Yeah, exactly.
and we can cache based on pointers, not strings, because also those comparisons, if we're using pointers, will be faster.
Yeah, like if we have like a huge string like in a cache, that would be not as good as just like an index, right? So.
Yeah. Okay. Let me try implement that out real quick.
Mm-hmm.
Uh, you do this too in the interview or no? Like build a class.
No, no.
Uh,
I never got asked DP in any interviews.
I've never been asked DP in my life in an interview. It's
If I get
crazy.
asked this kind of stuff, though, yeah, I don't know. I mean, I could code this in like 5 minutes, so I'd have to think about, all right,
Yeah.
how do I like pretend to think about it or something? I don't know.
Um, where's your text one? Text two. Let's say pointer one,
Okay.
pointer two. So we have these, and then we're gonna be storing a cache.
Mm-hmm.
So the same thing is our base case, right? If text one, if the length of text one equals 0, or the length of text two is equal to 0, we just return 0, right? Because there's nothing we could do here.
Yeah.
That's the base case. 0 as in the longest common subsequence is 0.
Mm-hmm.
And then now let's work through our case. But like if text 1 0, or sorry, no, we're working with pointers here. So we pass in the pointers here.
Mm-hmm.
If these are actually equal to each other, then we could just return, but like, definitely store something in the cache here. Else pass.
Mm-hmm.
This is the other case they don't equal, but if they do, we'll say recurse self or sub result would be self dot. We're gonna call dp on the same variables, which is these ones.
Mm-hmm.
We're gonna increment this one, and then we're gonna increment this one. But then we're also gonna do like 1 plus this.
Yep.
I'll do like sub result equals. Okay, what are the other results here? So this essentially means like yeah, we're since they match, we're gonna it counts as a like A and A, so that we're gonna add 1 to the result. But then we're also gonna like do a DP there. There's only one option there really. But what's the other case? What are the two cases here that if they're not equal, we need to try text 1 or remove from text 1. And then we could also remove from 2.
Mm-hmm.
And then from this, we're not actually matching anything, I guess. So we don't add 1 here. But what we'll do is like if we remove from 1, we just increment that pointer, and then maybe they'll match down the line, or like maybe the next recursion might match. But let's do. So we either move the +1 here, or we remove, or we cache, or we move up this one,
Mm-hmm.
and then we take the sub result should equal to the max of remove from 1 and remove from 2. We want to maximize that value.
Mm-hmm.
And then after, we could just return the sub result. And then we could just introduce a cache as well by doing cache. And what are we storing here? Probably a pointer of, if we get to these 2 pointers, then we know the result. And then we do the same thing. We just cache this as well. If these are in the sub result, return sub result. Oh shoot! What happened?
I don't know. It just got deleted.
If does it making sense so far? This part, if
Yeah.
if the pointer is in cache, return cache. Something like this.
Mm-hmm.
It's like base case, cache, recursive case.
Mm-hmm.
And then here, now we just need to implement this. I mean, like we could just call solution here and then have default values.
Yeah, I guess that also probably works. Yeah. Never seen anyone do it this way, but it makes a lot of sense too.
Yeah. How's that look?
So yeah, I would try running this one because you have some bugs, and then see
Oh,
what
really?
happens.
Okay, dry running this one. Let me see. Okay,
Or you can
let's.
dry run it. Yeah, that's fine too. I was gonna say you can just run it, but you can dry run as well.
What's the name of this question? Is this a LeetCode question?
Mm-hmm.
Let's see. probably done this one before. What's
Yeah.
the name of the question?
It's called longest common subsequence.
Oh yeah, this is classic. Wait,
Classic, yeah.
I did my thing. Let me log in. Let me log into my LeetCode.
Mm-hmm.
Yeah, I probably did this question for sure.
But your bugs are kind of like they're not logic bugs. They're just kind of like silly bugs. So.
Okay, wait. Let me look at here.
Mm-hmm.
So result. Let me just dry run it because
Sure.
let's start with a simple case of we have a or we have text one equals
Mm-hmm.
a text two equals a.
Mm-hmm.
I mean, like we have pointers at 0, 0, and then we'll just build up this case. We'll do p1 equals 0, p2 equals 0. So when we call this function, if the length of text one equals 0 or we return 0, that's not the case. So we go here. The pointers are not in the cache, so we return cache. I think that's fine.
Mm-hmm.
Then we have sub result is equal to none. So if the text one pointer is equal to the text two pointer here, okay, because we're going past it a bit. Wait, let's see. Oh, okay. If the pointer we're doing like if the pointer is greater, if the pointer one is greater than or equal to, that means we're out of bounds.
Mm-hmm.
Is that the one you're thinking?
Yeah. Yeah, because you were just checking for the length of the text. You weren't
Yeah,
actually looking at the pointers, so you would never hit a base case.
yeah, you're right. Equals length of text two. So if the pointer two exceeds that, so these get incremented.
Mm-hmm.
Yeah, no, I think that would work. I don't know. Should I run it?
Yeah, you can run it. I think you're
Okay.
good. Yeah, I mean, you might have something else, but I think this looks good.
Longest.
And then I mean, from here, it's just going to be like syntax errors. Your
It's
logic's
called
fine.
longest common subsequence.
Yeah, it's 1143.
I need to log in. Okay. Can you run it on yours?
Yeah, let's see. I can.
Yeah, I have to log in.
I think it was called something else. Yeah, longest common
Let me.
sequence. I mean, I think the names are also different, so maybe I have to like change some of this. Uh, here. And you have like pointers and stuff, right? So
Yeah.
this is base case.
Let me just
Okay.
log in on the side.
Okay. Pointer 1, 0. Pointer 2, 0. Cache. See if there's any other problems.
Okay, wait, I got it up here.
Okay.
Yeah, it looks like I solved this question back in 2024. Not that long ago. How did I solve it? Is it unoptimal? Let's see. Yeah, is this kind of similar? Interesting. No, that's a good question.
So it says for A, B, C, and D, E, F. Yeah, I don't know if I just called it incorrectly or what.
Well,
For
I
A,
even
B, C, and D, E, F, you got 3, and that expects 0. I mean, I think you did it right, so I don't know why it's giving me the wrong thing.
it's funny. I even named the variables the same. Pointer one.
Yeah, there's no way, unless I labeled it something wrong or something. Yeah, I don't know. Did you try running it on your end?
Let me try it now.
Okay. Yeah, the example 3 failed, but I think you did it right, so I don't know why.
Yeah, sample three. I output three when it should have been 0.
Mm-hmm.
How did I get 3 there?
I have no idea, to be honest. Like, the logic's right. I mean, this is where you can just throw it at the GPT and it's like some dumb thing. So, let's see.
Wait. Why am I adding 1 here?
Yeah, like, all your stuff's right. It's literally just going to be below. Change default.
Like, how is it
Potential
adding
side
1?
effects that from multiple calls that share the same default dictionary. Yeah, so there might be something with you having that cache like this. Not sure. It might be something there, but it didn't find any logic errors, so let me run the one it suggested. Yeah, so the one it suggested is all correct. Oh, I think it said cache. Yeah, so it literally just changed like some Python syntax thing, and that was it.
Yeah, maybe if I called this from a helper function.
Yeah, so it literally just said cache is none, and then when the cache is none, then it makes one, and that was the only difference, and then that worked. So it might be some like reference or something that you're like reusing across calls or something like that. But I mean, the important thing is all the actual code is correct. It's literally
Okay.
just like that part. Okay.
Okay. How's that?
Yeah, I think it was pretty solid. I think you noticed that you want to use pointers. Maybe you had a little bit of trouble figuring out that like you can't just say like I want to use a letter and then scroll through the other word. Like you want something better.
Yeah.
But once I gave you a hint, I think you figured it out pretty quickly. So that was good as well. And then you found, yeah, you also figured out that when the letters are the same, you always want to take the letters. I don't think everyone comes up with that. Yeah, so I think it was pretty solid. So I would just keep doing problems and then, yeah, just keep doing top down. And then, yeah, I think the next thing is going to be for you to recognize problems or DP, and the tricky problems are the ones where the states aren't obvious. Like all of these states were really obvious.
Yeah. Yeah. Let's ramp it. Let's keep going. On a different one. We'll start from here and go even harder. DP
Yeah,
question.
cool. Yeah,
The
so we
hard
can
part
do
is
this.
figuring out if it's DP though. That's the thing.
Yeah, so like I said, the main things for DP is if you're taking or not taking an item, that's a big hint, and if things aren't contiguous. Because
Yeah.
DP is literally like, I'm going to go through every index and like have a decision. So I think that's the part that makes it kind of easy, I want to say, is like here, you can skip a letter or you can take a letter. So anytime you have that, it's like almost always DP.
I see.
Or like, yeah, so just not contiguous. And then also, like I said, if you don't know if it's DP, if you just fill out these three things, the base case, the state, and the recursive case in like pseudocode, and figure
Yeah.
out time complexity, then you could figure out like, okay, can I do this with DP?
I
And
see.
then yeah. And then if it's too big, then you can't. So that's the other thing is like when you create your states, sometimes they'll be too big. So like really common LeetCode constraints are like 10 to the fifth. So you can't have two states that are 10 to the fifth because that'll be too big and that will give you like TLE.
I see.
So yeah, things like that.
Cool.
And then figuring out how to take maybe some simple states they give you and make it things that will actually fit. So yeah, we'll definitely do like maybe some hard DPs or something in the next one. See how you do
Nice.
those.
Okay. All right. I'm gonna end the video here. Thanks for running that.